In this video, we're going to talk about some of the special considerations we have when gravity is our force that's causing things to go around in a circle. When that happens, we call it orbit. So here's our first problem. In this one, we have a figure shows two planets of equal mass that are orbiting around a star in a counterclockwise direction as shown. So this is our omega. From the point of view of the observer on each planet, the planets appear to orbit each other while orbiting the star. So this is very similar to, say, like the moon and the earth. We orbit each other, and then we're also orbiting around the sun. Now, since the moon is much smaller than us, it mostly orbits us, but the earth does wobble. If the two were the exact same mass, then we would orbit around each other around a center of mass point, and that's what's happening here. This X point is the center of mass of the system. Now here's the deal. This is a system that's orbiting, that's going around in a circle, so all of our rules for circular motion still apply. Now, draw and label an arrow to represent the direction of the net force on the center of mass of the two-planet system. Well, it's the same as it always was. The object is going in a circle, or the system in this case is going in a circle, so there must be a force towards the center. Now, don't label it FC, label it what it is, which is gravity. Our second question says, draw arrows to represent the acceleration and velocity of the system's center of mass. All right, so the force is towards the center, it's accelerating towards the center. It's not slowing up, it doesn't give any indication that it's slowing down or speeding up at all. So it's just towards the center. And then our last one would be the velocity. Velocity is always tangent to the path. So there's our velocity, just like before, just like any circular motion problem. Question number 2. Two satellites are in circular orbits around Earth, satellite A and satellite B. A has a velocity of VA. What's the speed of satellite B? They're going in a circle, so let's use what we know about circular motion. We know that the sum of the forces towards the center equals MAC, and that force in this case is gravity, so that's the force of gravity equals mv squared over r, and that force of gravity is big G, the mass of the thing in the center, which would be Earth, and then the mass of the thing going around, and then the radius of the orbit squared equals the mass of the thing going around, v squared over r. Now notice we have some things canceling out. The radius, one of the radii, cancels over here with this one, and the mass of the thing going around in the circle, the planet, or the satellite in this case, cancels out. And so we end up with an equation that looks like this. V squared equals G, mass of the Earth over the radius of the orbit. And we can square root both sides, and this would just be V. And we can see that G and the mass of the Earth don't change for the two different satellites, and so therefore V is proportional to the square root of 1 over r, orbit. Okay? Now, satellite B has, what does it say, 3 times the orbit. So if it's 3 times, that means that the velocity would be 1 over the square root of 3 times the original, or that the velocity of B would equal 1 over the square root of 3 times VA. And there's our answer. Next problem. Planet X has 3 times the mass and 9 times the radius of Earth. The magnitude of the gravitational field. What the heck is gravitational field, everybody? Do you remember? That is just little g. The acceleration caused by gravity and gravitational field are the same thing. So what is that for the mysterious planet X? All right, so first of all, we need an equation that tells us what little g is. All right, the way I derived it in class is I said that the force of gravity in general equals the force of gravity weight. So that is big G, mass of the planet, and then mass of the thing on the planet, divided by the radius of the planet squared. And that must equal mg, weight, equals the force of gravity. And this is the thing on the planet, so that means G equals big G, mass of the planet divided by the radius of the planet squared. All right? So what's going on with our particular planet? In our particular planet, what's changing? We're changing the mass and we're changing the radius. G, gravitational field, is proportional to the mass of the planet divided by the radius of the planet squared. Now what are we doing? We're changing the mass 3 times bigger and the radius 9 times bigger, but that's squared. So we end up with a 3 in the numerator and a 9 squared in the denominator. That gives us what? 3 over 81, which gives us, what is that? 1 over 27. That means G for planet X would equal G for planet Earth 1/27th of Earths. There we go. For our next problem, the magnitude of the gravitational field on the surface of a planet is 2G, twice Earth's. The planet's mass is 3 times the mass of the Earth. What is the radius of this planet? All right, so we've already derived this equation. It's G equals big G, mass of the planet, divided by the radius of the planet squared. But we want to solve it for radius. So let's rearrange it, and we end up with radius equals gm over little g square root. Now what are we changing? We're saying that the planet is 3 times that of Earth, so that has 3 times the mass, and we know that G is twice as big as Earth's, so that means that this planet over here would have the square root of 3 over 2 times the radius of Earth. So the radius of this mysterious planet is equal to 3/2 the square root radius Earth. There we go. Our last problem is a free response problem. And in this one, we have a spacecraft in orbit. It's going around clockwise like this. There's a radius r, and the mass of the Earth is me. In the first part of the problem, it asks to draw the forces acting on the spacecraft. Do not draw components, it says. So they don't want any like X or Y components. They just want the actual forces. Now, it's going in a circle, so there has to be a force towards the center, and our only force is the force of gravity, and that's it. For our second part, it asks us to derive an equation for the time period of the spacecraft as it goes around. Okay, so this is pretty intimidating for students, but just start writing down what we know. What do we know? We know that it's going in a circle, so the forces towards the center must equal MAC, and that force towards the center is gravity. So we have gravity, mass of the Earth, mass of the satellite over the radius of the orbit squared. That's the force of gravity. That equals m, the thing in orbit, and v squared over r. Oops, that's the radius of orbit. So that cancels, that cancels, that cancels, and that cancels. So we're left with the same equation that we had earlier, which is v g, mass of the Earth, over the radius of the Earth. Actually, they're just calling it r, so let me just write it the way they do. Always write it the way they ask you to write it. Uh-oh, we're out of focus again. There we go. All right, well, that's not good enough. We need time period. So I need an equation that has time period in it. So let's see. We do know that the time period is related to the velocity. So the velocity in orbit, if it's a circular orbit, is a circumference, 2 pi r in this case, capital R, over the time period. So if I square this thing, I can substitute that in here, and what I will get will be 4 pi squared r squared over t squared equals g, mass of the Earth, over the radius. Okay, so now let's check to make sure that we have the variables they want. We always need to check that. So it says that our answer needs to be in terms of m. Okay, well, we don't have any. Mass of the Earth, okay. R, okay, so let's see, M, R, R, physical constants, okay, 4 pi is a constant, G is a constant. So there we go, time period in terms of the things that they asked for. So we can actually quit right here, or we can pretty it up and resolve it to make your math teacher proud, but the thing is that really we're done. So we can leave it like this, but if you pretty it up a little bit, you can get t squared equals 4 pi squared r to the third over g m e, and that's generally the way we see this written. For our last one, it says, or last one on this page anyway, it says a second spacecraft of mass 2m is placed in a circular orbit of the same radius r. What does that do to the time period? Well, the answer is, look at our equation. 2m. Oh, that's the wrong m. That's the mass of the Earth. I don't see our little m because our little m canceled out way over here, which means that it's irrelevant. It doesn't make any difference. So the answer is it won't change. It will stay equal to what it was before, and your brief explanation is the mass cancels out. And that's all you need to write. The last part of the problem says the first spacecraft is moved to a new circular orbit that has a radius greater than r. So it's moved outward to a new radius. Is the speed of the spacecraft in the new orbit greater than, less than, or equal? Well, hey, we can just go back to what we had before, and there is our velocity. So I'm going to rewrite that over here. V squared equals g, mass of the Earth over the radius of the orbit. And we can see from this equation, as the orbital radius goes up, the velocity has to go down because it's inversely related. V squared is proportional to 1 over r. So it must decrease. And that would be our explanation as well, that they're inversely proportional. If you want to get technical about it, V is proportional to 1 over the square root of r. So as r goes up, V has to come down. Now, I know some of you may be asking, but wait a minute, I tried to solve it this way. Doesn't V also equal 2 pi r over the time period? And you're absolutely right. That is true. The thing is that these two are constants. R is increasing, but we do not know what is happening to the time period. That is not a constant. So V is proportional to R over the time period. And while this is going up, we have no idea what's happening to the time period. So there you go, everybody. That's how we incorporate gravity as our central force, or the force causing something to go around in a circle. And we had come up with a couple of unique equations for time period, for orbit, and for the velocity of something going around an orbit. And we also discussed how you find the gravitational field around an object. We're all done.